Today's problem is from Introduction to Electrodynamics by David Griffiths, and it is from the 4th edition. The problem states that we need to find the electric field at a distance z above a flat circular disk of radius r that carries a uniform charge of sigma. What does your formula give in the limit r tends to infinity? And also check the case for z being much greater than r. Okay, so we basically need to find the electric field at point P. All right, so we begin this problem by taking into consideration the infinitesimal areas, thus patches, that are present in this flat circular disk, All right, so let's analyze what these dAs, these infinitesimal areas, are. Okay, so if we go to spherical coordinates, then we would notice that if we have this coordinate basis of I'm gonna notate that the radius is represented by s hat, and the angles are denoted by theta hat. Okay, so this small patch of area would be represented by this change in distance times this change in distance, and this over here is basically s d theta. Okay, and this one is ds. All right, therefore we can say that the infinitesimal areas are s d theta ds. All right, so now what we're going to do is we are going to apply the formula for the total electric field, which is sum of the infinitesimal small electric fields that can be derived from Coulomb's law. Okay, so from Coulomb's law, we know that the infinitesimally small areas is basically k dq all over mu cubed times mu hat, where here mu is basically the displacement vector that separates the point P over here, from our given infinitesimal at this point. All right, so this is a displacement vector. All right, and of course dq is our infinitely small charge, infinitesimals, actually, the infinitesimal charges. Okay. All right, so in order to find the total electric field, we take the integral. Okay, so this would basically be the integral of k dq mu cubed times the vector mu. All right, now we also have this information that states that the surface charge density, which is sigma, and this is uniform, of course, this is basically dq all over dA, right? I should write this down as dA. All right, and from here we could say that dq, as given over here, this dq can be written down as sigma times dA. All right, and now we have an expression for dA as well from here, so we can finally write dq as being equal to sigma times s d theta ds. All right, now plugging these things into the total electric field E, we get that the total electric field is basically the double integral, since we have two variables d theta and ds, the double integral of k sigma s d theta ds all over s squared plus z squared all to the power 3 all over 2 times this vector mu over here. Now, before I write down the vector mu, let's try to find out what it truly is in this case. All right, so the vector mu is basically pointing from this position where you have the dA towards point P all over here. Okay, so how do we find this? In order to go from this point, let's say this point A, to point P, we basically need to go in this direction, which is negative s hat, and then go up by z hat. Of course, here S represents the radial distance from point A towards the center. Okay, so we basically now have that mu is basically negative S hat plus z hat. Okay, and that's how, of course, I got to this. I should have been more clear over there. The magnitude of mu is s squared plus z squared to the power 1/2, and from there I got that this is the magnitude of mu. All right, so we plug this in over here, and then we get that this is negative s hat plus z hat. All right, so now if we write things down by separating the integrals and also putting in their limits, we kind of get a scenario where you can pull out these k sigmas outside, since these are constant. All right, and then you have an integral that kind of looks like this. Then you have 3/4 over here, not 3/4, 3.5, 3 all over 2 times you have negative s hat plus z hat d theta. And as you can see over here, this theta spans from 0 to 2 pi, right? Since you're taking this entire revolution over here, right? So theta spans from 0 to 2 pi, and your s, the radial direction, the radial distance, spans from 0 up until a capital R. Okay, so you have the limits from 0 to 2 pi, and the distance s spanning from 0 to R. All right, now the tricky part is this integral over here. We cannot just pull out the s hat outside, okay? So what do we really need to do? First of all, let's try to think about why we cannot pull out the s hat. See, s hat is one unit vector over here, and you have z hat. First of all, you could also think it like, well, it would be better for us to deal with things in Cartesian coordinates. And secondly, like, you cannot pull this s hat vector out because it has a dependence on the theta over here. All right, and it's hard, it's generally not easy to deal with. So let's convert this s hat into Cartesian coordinates. Okay, so s hat in Cartesian coordinates is basically cosine of theta x plus sine of theta y hat. All right, cosine of theta x hat plus sine of theta y hat. All right, now we are going to input this into this integral over here. So you basically have that negative s, I'm using different n, times s hat, which is cosine of theta x hat plus sine of theta y hat, right, plus z hat, all right, and this entire thing is multiplied by d theta, and this spans from 0 to 2 pi. Okay, and if you simplify this, then you get something that kind of looks like this. Negative s, because this has no dependence on theta, negative s times cosine of theta d theta x hat minus s sine of theta d theta y hat plus z d theta. All right, and everything spans from oh, I should add d theta over here as well. D theta, and yeah, so everything spans from 0 up until 2 pi. Okay, now you can work this out on your own, but these two expressions, these basically go to 0, and you finally have only this left, and this just basically stands for 2 pi z. All right, now this is the value for this second integral all over here. So you finally have that the total electric field is basically the integral that is multiplied by k sigma times s ds all over s squared plus z squared all over this to the power of this times 2 pi z. 2 pi z, and the bounds being from 0 to r. Okay. Oh, I also need to add the z unit vector all over here, because of course this has a unit vector all over here. Okay, so you can pull out the 2 pi z outside because it has no s dependence, ds dependence. So you finally get 2 pi z times k sigma, and you are left with this integral over here. Now, you can do this integral by hand, or you could use a computer, but if you just plug in this integral into any website, specifically one specific website that I use is Integral Calculator, you would get something that looks like this: 2 pi z k sigma times negative 1 z squared plus s squared raised to the power 3 all over 2, taking the limits from 0 to r. And finally, you get that the vector E is basically 2 pi z k sigma 1 over z minus I need to say that this should be 1/2, and this should be 1/2 as well, z hat. And this is the total electric field at the point P. Now, we also need to analyze what it looks like for the case when r tends to infinity. So, case r tends to infinity. Okay, so for r tends to infinity, what really happens? You see, for r tends to infinity, we have that this quantity over here basically goes to 0, right? And so this implies that E is basically equal to 2 pi z k sigma, right, times 1 over z minus 0, right? So the z's cancel out, and you get 2 pi k sigma z hat. Now you can also modify this by expanding k being Coulomb's constant, right? This is 1 over 4 pi epsilon naught. So you basically get that 2 pi sigma all over 4 pi epsilon naught z hat, right? So this is the case for E being r tending to infinity. All right. Now we also have this other case where z is much greater than r. Okay, so if z is much greater than r, let's see what happens to the binomial expansion of this term over here. So for z much greater than r, we have that z squared plus r squared raised to the power negative 1/2. Negative 1/2 is basically z squared raised to the power negative 1/2 plus negative 1/2 times z squared raised to the power negative 3 over 2 times r squared. Okay, and dot dot dot. We're going to ignore those other terms, and we write this down as 1 over z minus 1/2 times 1z squared times r squared. Now one might ask how I got to this. This is basically the binomial expansion. And this is basically, this basically looks like this. So if you have two quantities, a and b, raised to the power n, then you can write this down as a raised to the power n plus n, a to the n minus 1 times b plus dot dot dot. I should also write the next term down. It's n minus 1, a to the n minus 2, b to the 2 all over 2 factorial plus dot dot dot. This is just the binomial expansion. Okay, so we have this. Now plugging it in for this case where z is much greater than r, we have that this is equal to 2 pi z k sigma times 1 over z minus 1 over z plus 1 over 2 z squared r squared. Okay, of course, z hat at the very end, and this basically simplifies into the following form. So you have 2 pi z, k can be written down as 1 over 4 pi epsilon naught, and there's sigma, and there's r squared over here, and then you have 2 z squared z hat. Now, you can simplify this even further. That's all up to you. I'll write this down as sigma r squared all over 4 epsilon naught z z hat. And this is the case for z much greater than r. I should also isolate the term that gives you e when r tends to infinity over here. Okay, so that's all.